another minute or two?
Sorry, so I'm Cameron McNatt. I'm the Managing Director of Motion Energy. Thank you all for joining us this morning. So myself and my colleague Richard Knox, who's the MD of ECOG, are going to tell you about a project that we're doing with the OGTC, as well as with partners Chrysor and Modus, called Renewables for Subsea Power. I'll let Charlie Booth kind of start. Charlie Booth from the OGTC tell you a little bit about the OGTC and these projects.
Cool. Thank you, Cameron. Welcome to everyone who's joining us, by the way. Thank you. We do appreciate you taking your time to come and listen to us. You'll be pleased to know that I'll be doing very little talking today. I'm just giving just a few sort of introductory pieces before the session kicks off. So just to let you know, this session is being recorded. So if you're uncomfortable with that, then we ask that you leave the webinar now, and then the recording will be made available to people afterwards. As attendees, you are all muted with your cameras off. There will be opportunities to ask questions, and we encourage you to do so. So you'll be able to raise your virtual hand at certain points throughout the webinar, and then we'll unmute you, and you can ask the question directly. Or you do have the chat function, which is next to the raise hand button, should be at the bottom of your screen, and you can just put anything in the chat at any point, and then we'll address those as we go along. We do hope that there's no connection issues today, but if you are struggling to hear us, sometimes if you turn off some of your other applications using up memory and bandwidth on your computer, that can sometimes make it run a bit more smoothly. So just a very brief introduction. So OGTC are a not-for-profit government-funded organization that fund technology development to save costs and help the oil and gas industry reach a net zero carbon future, which is something that I think this project really sort of plays to. So this project is being supported through the Marginal Development Solution Center, and it's being done, as Cameron just said, between ECOG, one of our first projects ever when we were set up in 2017 were with them, and that's in collaboration with Motion Energy, who came through our technology accelerator, our TechX cohort 2, and being sort of heavily supported by Modus and Chrysor. So a very sort of collaborative project looking at applying renewables for the oil and gas industry. So do hope that you are all safe and well wherever you are. And I'll now hand over to Cameron, who will take us through it. On you go, Cameron.
Great. Thanks, Charlie. So again, Cameron McNatt and Richard Knox, and we'll be presenting to you this morning. We will go through the presentation. We'll have some, but we'll essentially save questions for the end of the talk. So I'll start with a story. Back in the early 1990s, Maersk Oil, which is now Total, was looking to develop the Ranar field in the Danish sector. Ranar had about 6 million barrels of oil, but it was located 13 kilometers from the nearest platform, and they expected it to only last about 3 years, so that making it a very marginal development. But being resourceful, Maersk found that they had available a 20-year-old column buoy, which is a buoy for offloading oil onto a floating production system. And they repurposed this buoy as the world's first control buoy. So they refitted it in the early 1990s to be an umbilical-less system for controlling subsea equipment, which made the cost of developing the system independent of the distance of the tieback. They retrofitted it with 2 7-kilowatt diesel generators, as well as UHF radio comms for controlling the wells. And while they only expected to use this for 3 years, it turned out that this field was much more productive than expected. And it ended up lasting more than 12 years. And over that 12-year period, they only had 1 failure due to the control buoy, and that was due to the diesel generators. So the system actually proved, 20 years ago to be, almost 30 years ago, to be very, very reliable of a system. And so what we're proposing now is something, conceptually actually very similar to that. We're proposing to use renewable energy, Motion's Blue Star wave energy converter for providing power, as well as a communications hub, and then ECOG's HALO subsea energy storage system for storing that renewable energy and distributing the power and communications to subsea equipment. The applications include subsea production systems, residential ROVs, and autonomous underwater vehicles, various sensors and monitoring equipment, and it can be used for a variety of offshore energy applications, greenfield, brownfield, and lots of decommissioning applications. And the aim of the Renewables for Subsea Power project is to qualify what we call an RSP system. So the presentation today is broken into 3 sections. The first will just describe the RSP system and some of the work that we've done so far. We'll talk through the applications where the RSP system can be used, some case studies that we've done, and then we'll finish off talking in more detail about the actual project that we're doing with the OGTC. So the system that we're working on for this project consists of Motion Energy's Blue Star 1 wave energy converter, which you see in the center of the figure, that yellow thing. ECOG's HALO battery system, which is an energy storage subsea battery system, as well as a comms gateway. Chrysaor is actually the UK's largest oil producer, and they are providing a subsea control module. So that is the part of the Christmas tree it's essentially the sort of brains of your subsea production system. So while the picture actually shows a Christmas tree, we don't actually intend to test with the Christmas tree. We'll just test with the subsea control module. And Modus is supplying its residential hybrid autonomous underwater vehicle. And so you can see at a very high level what the system is. So we have the wave energy converter that's controlled remotely via wireless comms. Is providing power and relaying that comm signal to the ECOG system, which is relaying it to either the production system or the residential AUV. Motion Energy designs wave energy converters. Our focus is on the geometry, and we've developed a programmatic geometry generation that produces geometries, runs them through a fast simulation, and then we incorporate into that an optimization routine that optimizes to find the best system. So that's really our focus as a company. That's what we do. And we're developing the Blue Star, which is a specific wave energy converter designed for subsea equipment. So Blue Star generates an average power of 5 kilowatts in the North Sea. In the North Sea, it will be controlled and communicated with using the 4G TampNet network, as well as having a satellite comms link. It's designed to be reliable. It has just a single hinge, and we're developing a robust powertrain, trying to go either direct drive to a generator or through a magnetic gearbox. And it's also highly survivable. So you see on the front and back, it has what are called wave channels. These help in the performance, but they also aid in the survivability. The forward wave channel causes the machine to dive through steep waves, just like a surfer diving through waves. We're also focusing a lot on the mooring and installation in order to make it easy to install. And we've also designed it to fit into a shipping container to make for easy logistics. For this project, we'll be using our first generation prototype Blue Star 1. Blue Star 1 is being built with funding, a £3.3 million project from a funding body called Wave Energy Scotland. It has a nominal 10 kilowatt generator. It's fitted with 3G, 4G, and Wi-Fi for wireless comms. It has built-in energy storage, 30 kilowatt hours, and it's capable of remote operation, meaning that you can have someone sitting on shore at a laptop controlling and diagnosing problems. So far, we've built the generators and the electrical systems, and they've been tested on a bespoke test rig. Fabrication of the main structure and the assembly is now back underway after a bit of a hiatus related to COVID. And we're expecting to launch our prototype this autumn and test at the European Marine Energy Center in Orkney over the winter. With that, I'll pass it to Richard to talk about HALO.
Thanks, Cameron. So I'm Richard Knox. I'm the Managing Director of ECOG. So just to give you an overview of the HALO energy storage assembly, HALO is essentially the gateway to the subsea infrastructure. It powers subsea assets. So we're using an advanced lithium-ion energy storage system, while at the same time utilising our intelligent energy management system to recharge the onboard batteries. So this can be achieved in a number of ways using energy harvesting sources, such as Motion's Blue Star wave energy converter, which we're discussing today. So this ensures that the subsea equipment is always supplied with a clean, stable power supply. In order to facilitate the highest level of integrity, HALO adopts the same environmental barrier philosophy as you'd find in a subsea control module. So with our IAMs, we have the equivalent to a subsea electronics module. It's contained within a 1 atmosphere housing, which in itself is contained within a dielectric fluid and pressure balance within our electrical distribution unit. The battery modules themselves are contained within standard 60 kilowatt hour battery housings with dual independent testable seal assemblies. And the electrical distribution unit allows HALO to accept multiple input and output connections for full integration flexibility and to operate multiple equipment at the same time. There are dual communication paths through HALO, and there's a further slide which explains this in more detail. From a mechanical packaging perspective, HALO utilises a road transportable subsea protection frame. And from the Renewables for Subsea Power project, we've utilised some of the spare space to allow us to mount an SCM for the trell. This would normally be mounted on the tree, as Cameron mentioned, on the manifold. And we've also included an umbilical clamp assembly, which gives us a kind of small compact assembly for the next phase of this project. So we've just moved to the next slide. Yeah, so the other key assembly under consideration for this project is the AUV dock. And this is used to support the Modus hybrid AUV. And this is based on the Saab Sabertooth, one of the most advanced AUV systems available. So this provides an autonomous survey and inspection capability. The AUV has the capability to be configured with advanced and variable payload to meet standard and bespoke survey specifications. And from a manoeuvring perspective, the AUV has conventional and hovering autonomous functions with 6 degrees of freedom. It can be docked using the subsea docking station as interfaced with HALO, or it can also use a surface dock. The AUV can harvest high resolution, high quality data at high speed. Modus are in the process of developing the next generation of equipment with vehicle AI and operational management programs. Further developments also include the ability to complete light intervention capabilities. The next one, Cameron. Yeah, so within the WEC HALO configuration, there are 2 means of communications, 3G and through water acoustics. The primary system used is a local area network, which reaches from the seabed to shore. It's Ethernet based, however, at certain points, the network switches protocol to allow data transfer, namely a 3G link between shore and the WEC, an SHDSL between the WEC and the seabed. On the seabed and on the WEC, the Ethernet based network allows any device with an independent IP address to be connected. Permissions are then granted by the network administrator to any device owner to access their device remotely via VPN to the current 3G router and onwards into the local area network. Only users granted access can see the LAN via the secure login. So any user of the local area network can keep their information secure if they're able to encrypt the information before transmission and then decode at the receiving end. As the system acts as a network, the information is transmitted along the same physical path simultaneously with data transmission. and rates being limited only by the 3G link to shore. What this does is that it facilitates an invisible link to shore whereby information can be routed onshore to subsea equipment and vice versa with no interruption and completely securely. The onshore operator can route commands or missions in exactly the same way as they would had a hardware connection been used. Health monitoring information is also being logged all the time and can be relayed in real time if required. All devices, including the HALO, will use the local area network as a primary communication route. HALO, however, does have secondary acoustic communications should the local area network fail, but this comes with a significant reduction in data rates. In the example that we've used, and the one that we've been developing, in terms of the connection between the WEC and HALO, in this setup we've provided two comms lines. This provides a level of redundancy. There's also a single power line which transmits power from the WEC to the HALO system in AC and is converted to DC to charge the batteries. And this is exported appropriately to the bands of the subsea equipment, either AC or DC, whatever the equipment requires. And the system can also be configured to transmit power from the HALO back up to the WEC, or even further to the redundancy if required. Are you coming?
So I'll take you through a little bit about the mooring, umbilical, and associated operations that we've been working on. So the system was designed for a test site that we're calling east of Orkney. It's on the southeast of Orkney at 50 meters water depth. I've got some more information on this test site later on. We've done comprehensive modeling of the mooring and umbilical in the wave conditions we're expecting there. The mooring is a two-line spread mooring with a swivel to allow weather vaning. That mooring configuration was really designed as part of our Wave Energy Scotland development program. It's the actual umbilical and the interface between that umbilical and the mooring that was the focus of the Renewables for Subsea Power project. So the umbilical passes through the swivel with a slip ring, that's power and comms through the slip ring, and then follows a fairly, as standard as these things can be, a lazy S-type configuration with some connectors down to the HALO skid on the seabed. So far, we've storyboarded the operations to, with a particular focus on identifying key risks and also identifying key mechanical interfaces that need to be designed on our systems. Also, as part of the project, we have done some numerical modeling of the system. And the goal of this modeling is really to understand how the interaction of the power generation from the WEC with the energy storage with the subsea load. So the way the modeling works is we have various sea states represented by significant wave height, HS, and wave period, in this case, energy period, TE. We model the WEC power generation using what's called a power matrix. And we go through a time stepping routine where at each time step, a block of energy is produced that's equal to the power times that time step. And that's added to a battery storage module, which has an upper limit, which is essentially the size of the battery. And then again, at each time step, we model the power or energy used by a subsea load. And so really we could incorporate an arbitrary load profile with a given duty cycle. For this project, we didn't have that level of detail, or we chose to model it a bit simply by just applying a constant power. So this is showing that behavior. So on the top row of this animation, you see here we're just showing the wave height, significant wave height. In the middle row, we're modeling the power captured at each of those time steps for that sea state. And at the bottom row, you're seeing the state of charge of the battery system. So when it's flat along the top, we're topped up, we can't store any more power. And right now you're seeing a big dip. So this is showing an example where the system actually fails to supply the required charge for the entire time. So once it hits the bottom there, then you have zero energy stored in the battery, and essentially our system fails to meet the load. So we use this type of modeling to assess the performance of the system, the combined system. So, just to highlight some of the key results, when we looked at wave conditions in the central North Sea with a pretty large battery storage, 500 kilowatt hours, we found that the system could provide 3 kilowatts of power 100% of the time. So that's a base load of 3 kilowatts of power. But it could provide higher average powers, less of the time. So up to 5 kilowatts, which is our average power generation, 80% of the time. And the amount of power that it could provide is really dependent on the battery size. The more battery you have, the more energy storage you have to ride out these long periods of no power generation. So the specifications for this system are really driven by the tails. And by that, I mean the sort of extreme conditions. I'm pretty sure this modeling was over 20 years of data. And in that 20 years, the amount of time the system, would fail would be very limited. It wouldn't even happen every year. And so in this particular case, we're showing a 2-week period at the test site. You can't see the dates, but this is in June. This specific 2-week period when there was really low wave conditions over the summer, just like a kind of an anomaly. But I think the point of this is that if the loads can accept, some different states where if we can do a bit of management of how the power is used, the system could provide more power very reliably. So now we're actually going to ask the audience a question using Menti. Let's see. So if you would, could you go to menti.com and enter in the code 581382? And we'd like to ask you all what you think are the main technology risks. I'll give you all a minute to do that. All right, we got our first answer. Mooring integrity. Fair enough. Swivel ring. A lot of concern about the mooring, which is fair enough. I mean, it's a concern of ours, and it's something we've spent a lot of time on. So some other concerns about communications, performance in real world conditions, concerns about permitting and consents.
Also, Cameron, I think we've got one suggestion in the chat panel, a quick disconnect for maintenance.
Okay, cool, thank you. Yeah, I mean, again, certainly it's hard to capture everything that's going on, but another thing to point out is Wave Energy Scotland, the funding body that we're working with, runs a number of programs related to wave energy development. So we're in what's called the Novel Wave Energy Converter Program, but they're actually running one right now called the Quick Connection System, where companies are developing just that. So quick mechanical and electrical disconnect systems, specifically for wave energy, but also have use cases throughout marine energy. Cool. Well, I'll leave that up. So if you want to keep entering those in, you can still do so. But I'll hop back to the presentation. So that is the end of our first section. And now we're going to take you through a few case studies on specific system applications that we worked on. Richard?
Okay, Cameron, thanks for that. So in this example, we're looking at how we can apply the technology previously described to some existing infrastructure. So what we've done is we've used the base case 10-kilometre tieback scenario that Exodus have used for the OGTC's Tieback in the Future programme. And we've assumed that there's been some sort of electrical failure that's occurred in the main umbilical, and this has resulted in the well shutting in. So not in the infield jumpers, just in the main umbilical itself. So to set the context, we're also assuming that the wells have been operating for a number of years, and it's predicted that the wells will be ready to cease production in 5 years. So what we've done is we've completed a full life cycle cost analysis to bring the wells back online and operate the wells for the remaining 5 years. And we've looked at two methods. The first being the WEC and energy storage that we've just described, and the other is a replacement electrical umbilical. So not the full umbilical, just an electrical line that will re-establish power to the well site. And then we've also looked at the analysis in terms of variable vessel rates. I guess you're all aware that the oil price has been moving around, and vessel rates tend to track in a similar fashion. So we've looked at how this affects the two scenarios. But as you can see, the alternative solution promoted by what we're describing, the technology that we're offering, gives significantly more cost-effective solution and will massively reduce CO2 emissions. So the renewable system can also be installed much quicker. It also provides significantly more power than is required. So this could subsequently be used to supply power to additional or new drill centres. So we just move to the next slide, sorry, Carl. So in this one, what we're looking at is an extended tieback. So when we're talking about a new tieback, in this example, we're effectively recreating a modern day equivalent of Regna. And the example that Carmen described earlier in the presentation. So for this example, we're considering that the main export pipeline is available for reuse, which in the North Sea is, I guess, a perfectly feasible scenario to consider. The Christmas trees are hydraulic, but they could equally be electric. And we're also assuming that the chemical injection is mainly for startup and shutdown, so not particularly demanding from a chemical use perspective. Now, although we've only assumed 2 wells are used in the system, the system that's powering the hydraulics, the electrical power, communications, chemicals, etc., could be supporting a 4-slot manifold or more. So the main factor here is that the equipment cost in this renewable solution is independent of tieback distance. And as such, there's huge savings to be had when we are considering a long tieback, greater than 80%. So the CO2 emissions are also reduced by an order of magnitude. And in general, the system architecture is very flexible for future expansion. And this could be very useful if you want to take, say, a phased approach to field development. Cameron, I'll just let you pick up on the next application.
So I'll take us through the next slide. So the next slide is about a residential AUV scenario. And for this scenario, we looked at specifically at Chrysaor's fields of Armada, Everest, and Lawmans. And we considered the range of the AUV basically by these blue circles. So, to give a bit of background, this is a fairly high level initial pass analysis. So for the range of the AUVs, we just considered the blue circles show the blue dots are where the docking station would be located. The solid blue show the distance the AUV could go out and then come back to its docking station. And then the dashed circles show the one-way distance, essentially double that radius. And we compared the deployment and operation of a residential AUV to a traditional annual inspection campaign, where we assumed that campaign would take place, would be for 20 days a year over a period of 10 years. We look at costs, including the cost of vessels, the operational expenses of the AUV and fees associated with that, the cost of the RSP system, both CapEx and OpEx. And what we found was that compared to the traditional system, the RSP system, not surprisingly, this is what it was designed to do, reduce the number of offshore days by 84%. But the cost reduction was pretty minimal. I mean, in our analysis, it ended up just being 1%. So costs ended up being about equal. But because the offshore days were reduced, it dramatically reduced the CO2 emissions by 8,000 tons, which is equivalent to 1,700 cars for 1 year. But what really, I think, was a key takeaway for us was that the AUV was only being used 20 days a year for that field inspection of Chrysaor's field. So that's only 6% of a year. But when you look at this map, already the deployment, the range of this was covering nearby fields owned by BP and Premier, including Mungo, ETAP, Huntington, and Shelley. And so this, kind of highlighted to us a recent article that was written by Elaine Maslin, where she speaks with a number of operators, including from Equinor and Chevron, and they are talking about this idea of an Uber of AUVs, where essentially you have AUVs deployed residentially throughout a field, and operators pay for their use as a service. So to us, we thought, with some strategic deployment of RSP docks throughout the North Sea basin, it would be a key enabler of this type of technology and business model. Okay, so we'll take you back to Menti to ask another question about the barriers of the technology. So now again, with that same code, you should be able to respond to this question if you don't mind. I'll give you all a couple minutes to do that. People? Yeah, I think that we need people to get it done, and risk aversion, absolutely. So the top three, all really interesting, is related to psychological factors of technology adoption. Water depth, that's a more technical one. Proof of reliable power delivery, that's kind of TRLs. Capability of the vehicle. So just to be clear, I guess when maybe this question wasn't clear, we don't just mean with respect to the AUV, we do mean that as well, but we mean it with respect to the system or any of the applications that we discussed, or any other applications that you could imagine. So reliability, attitudes, different specifications, that's a good one. Cool. Well, again, I'll leave this open for you all to continue to add stuff as you'd like, and just go back to the presentation. So this brings us to the final section of the presentation, where we're going to be talking more about the project itself. And I see that there's been a question related to the TRL, so we'll hope to answer that here. So the project, the RSP project, has been split into 3 phases. The first phase is a feed, which is essentially all we've done to date. And we'll speak to the TRL of the system. So not with not with respect to Motion's wave energy converter or Halo or the AUV, but we're talking about the TRL of the combined and integrated system working together. And we're using the 9-level TRL system that goes from 1 to 9, which is the version that the OGTC uses. So we completed the phase 1 feed this spring, which took the system to what we'd say is a TRL 3. So still fairly early on, but it was a good opportunity to capture the engineering requirements and progress the design. The next phase is the build and commissioning, where we will actually assemble a complete system and test it. And that will take us to TRL 5, and that's scheduled for this year going into next year. And then the final phase would be the actual at-sea field trial, which we intend to take the system to a TRL 7, where we'll install the WEC and test it at sea. I'll just talk briefly. I won't spend a lot of time on this, but we did do quite a bit of work in the FEED stage, raising the TRL from 2 to sort of, that is like an idea in our head with each of the partners, to a TRL 3. We've done a lot of systems engineering of power and comm systems and mooring and umbilical within the WEC. HALO, we designed a fit-for-purpose skid, various interfaces. We went through a sort of selection process, more or less what Chrysler had available for the SCM, as well as the electrical testing unit. That's been a bigger deal than expected. Working on the interfaces with the HAUV. As I mentioned, we've done quite a bit around operations in terms of storyboards and how things are handled. We worked on through these case studies, and then we've started to do various planning. So planning the project, considering the risks, working on the test plan, and then engagement is a really important part of all of this. So earlier in the year, back in February, before COVID was a thing, or was a big deal, at least in Europe, we held a workshop, which was really well received, to kind of get some feedback on our project and the test plan. And then we're obviously having this webinar. In phase 2, the build and commissioning, again, is to raise it from a TRL 3 to a TRL 5, is intended to take place running from August through March of next year. We'll finish off any sort of detailed design that needs to happen, and then fabricate or procure the various subsystems. Each of the subsystems will go through its own FAT. We'll assemble the systems into a complete system and test that at ECOG's lab in Aberdeen, which you can see some pictures of their lab on the right. The image on the bottom is actually Motion's generator test rig. I'm not sure that will necessarily be involved in the phase 2 testing, but just to kind of show an example of some of the test rigs that we've used. And we'll also, in phase 2, continue to push forward the actual operational and facilities planning that needs to happen to do the field trial in phase 3. So the phase 3 field trial will take the system to TRL 7. We will test actually in the sea, looking at roughly a 4-month period. The testing, again, as I mentioned, will be at this east of Orkney test site, for which consenting is well underway. So it was going to be the test site where Motion was going to test the Blue Star WEC for the Wave Energy Scotland program. However, because of delays in COVID, we're now moving to a different test site. I won't get into too much of that, but we have this test site that we've done a lot of work on available, and that's where we intend to do the testing. And it will focus on reliability and functionality. And just to talk a little bit more about that, so the kind of overall test plan, again, in phase 2, is to do the onshore commissioning in a controlled environment with the relevant system. So we'll have a power export cabinet from the WEC, which will be set up to simulate the sort of WEC power generation. We don't intend to actually bring the entire wave energy converter in for the testing, but we'll simulate the behavior of the wave energy converter, but we'll have the rest of the equipment there and test both power and communications in a lab. And then in phase 3, we have 2 different types of testing. Reliability testing, where we'll have Blue Star and HALO deployed for an extended period of time. It says 1 month, but I think we'd like to test for 3 months or longer. And we'll collect data on the waves, the power generation, the state of charge of the batteries, the comms, and then various health monitoring of the systems over that time period. And then we'll do specific functionality testing of the production system, the subsea control module, where we'll communicate with it and run it through a series of sort of test modes. So certainly better to speak to ECOG about that. And then we'll also do some functionality testing of the residential HAUV. So the HAUV would not be there for the entire multi-month test period, although the SCM will. But the AUV would be brought in for about a week to demonstrate a specific set of functionality testing, where we will sort of demonstrate over the horizon power and communications using the RSP system. So what's been the result of all this work so far, particularly of phase one? So in phase one, we've raised the TRL from 2 to 3, a small increment, but really what it's done is to de-risk the next phases. We've furthered the engineering, the test plans, and the project plans for the next phases, which will ultimately take the TRL to 7. We've demonstrated the system can provide 3 kilowatts of baseload power and higher peak powers. Sorry, it says 7 kilowatts, it should say 5. Case studies have shown that there's potential for really significant cost savings, greater than 50% in the umbilical failure scenario, but more like 80% in the long tieback scenarios, and then tremendous reductions in CO2 emissions on the order of 90%. The system has built-in redundancy, and that means that we have batteries on the seabed, and we have batteries in the WEC. And so, if the WEC were to go down, we still have those batteries on the seabed. And then there, as Richard mentioned, there are multiple communication channels, communication through the WEC, as well as through water communications built into the HALO system. And all of the RSP system can help enable new business models like basin-wide AUV networks. I think one of really the strongest outcomes of this work is that the whole is greater than the sum of the parts. So each of the companies, Motion Energy with its wave energy converter, ECOG with its HALO, Modus with their residential HAUV, they provide something that's valuable, but it's all made more valuable by us working together to develop a complete system that's a solution to customer problems. But we think there's still a lot of potential for further opportunities to optimize the system, both from an engineering and technical perspective, as well as operationally, how the operations and handling, as well as the business models of the various companies working together. And we believe the system, both the wave energy converter, the AUV, and the battery storage are really early days in the start of the technology development journey and the cost reduction journey. I think as many of you are probably well aware, there are tremendous cost reductions that are to be had that have been evidenced throughout various renewable technologies. This plot here showing that the cost of photovoltaics has dropped from $350 per megawatt hour to $50 in 20 years. So if the cost of our system and wave energy were to not drop dramatically over the next years, it would be the first time that's ever happened with a technology. So we think there's a lot of potential, and this is really just the beginning. And with that, that is the end of our presentation. We'd like to just leave you with one ask. We're looking for operators, tier ones, OEMs interested in supporting the project and being involved in the next phases. That would give you access to the test results and the design. And what we would ask is just for your feedback in the development of the system. And I don't have any more slides, but I will open it up to questions. So let's see. So I know you can, maybe the OGTC can help me manage the questions as well. I know you can raise your hands in the chat box. And also just to point out that it's not just myself and Richard up here. We have a number of people from the team, from Motion, ECOG, and Modus here to answer questions that people may have. So
yeah, absolutely. So so you've got sort of two ways you can submit questions. One is in the chat function, and the other one is to raise your virtual hand. So I think we had sort of a couple of questions that have come in sort of during the presentation that have been dealt with, but I don't think they were shared with all the attendees. So you know, just maybe run through those very quickly. So to start with, the simulation showed a fully charged battery at the start. How will the battery be charged initially?
so that, I guess that ECOG, do you guys want to say something about how the battery charging is handled?
I think Richard's trying to unmute himself. I can just see the like look of panic in his eyes.
Yeah, that's it. I've lost my cursor. But yeah, so basically the system can be installed pre-charged, or once we first install it, we can charge it up from a downline before the WEC's connected. So at the start of operations, the battery is fully charged. And I know some questions around the size of it. So the battery system that we've installed or looked at specking up for the trials 150 kilowatt, and Cameron showed the sort of optimum size is 500 kilowatt hours. The skid that we showed in the slides earlier on, that skid can handle roughly 800 kilowatt hours physically between that 2.9 meter wide skid. But the actual overall architecture can take up to 2.7 megawatt hours is what the IAMS is capable of controlling. But obviously from a cost perspective, you want to try and optimize the WEC power generation, the level of redundancy that you need in the system. So it's very flexible, but it's just a kind of trade-off. So so yeah, I hope that answers that question.
Cool. And then there's a question that's just come in at the bottom there from Nigel Robinson. So I think everyone can see that. So can you maybe?
Yeah. So that thanks Nigel. So in terms of the LCOE, I suppose the picture on the previous slide was maybe misleading because it was showing LCOE of various renewable technologies. From our perspective, for wave energy, more or less, if you're talking about LCOE, the bigger the better. I mean, there is an upper limit to how big we want to build a given wave energy converter, but we're talking more on the megawatt scale. The sort of cost of a unit of energy is not really relevant to this particular application when we're talking about subsea power. I mean, we don't intend to sell units of energy necessarily anyway, if that answers your question. Any other questions in the chat or hands?
Well, I suppose so one of the earlier questions was that you know, this session is being recorded and where will it be available? So you know, from OGTC side, so we'll aim to have it sort of up on our website and YouTube channel within about 2 weeks of today. And there was a question about, is it possible to get hold of the slides that we used in this presentation, which is sort of down to you guys?
Yeah, I think so. I mean, certainly if the presentation is going to be broadcast, I don't think there's too much harm in supplying the slides, but I will need to check with everybody.
Sure. Any other questions from anybody? I think you covered the TRL question, I think, quite well, Cameron. Any other questions from anybody? Another one from Nigel.
How long can it operate before you have to retrieve it to check it over? So short answer is yes, we have thought about that. I mean, for the wave energy converter, we're aiming to designing it for 3 years between planned maintenance cycle. It will also have built-in health monitoring systems, and our prototype has this for supplying, you know, health monitoring data back to operators on shore. In terms of how long can it operate before you retrieve it, that's really highly dependent on what actually fails. I mean, certain failures are more dramatic than others, which would require it to be retrieved immediately. But it also kind of relates to the built-in redundancy. So if it's powering something like a production system and you don't want that system to go down, basically if the WEC power generation fails, we still have the subsea battery storage that can continue to supply the power for a certain amount of time, depending on the sizing of that battery storage. And that will, drive how quickly the WEC needs to be retrieved and repaired. And there are also solutions where we could, essentially hot swap out the wave energy converter. So you go out there with a new one, take in the old broken one, and then just stick the new one on to bring this system back up more quickly.
Cool. Any final questions? No? Cool. Should we call it a day there then, guys?
Yeah. Well, thank you all for attending, and thanks for the OGTC for hosting the webinar, and of course all their support so far. And please get in touch if you have any interest in being involved in the project, or just any further questions in the future. So thank you very much.
Thank you, everybody. Take care.
Bye, guys.